Okay, so having completed the section, we now turn to the exercises. And you may remember that while going through the results of this section, we have in fact solved many of the exercises. To be more specific, we have solved the first 6 of them. So today we start with the 7th one. And here we have to prove that these given polynomials are, all of them are irreducible over the field of rational numbers. That's because in showing that some real numbers are constructible or not constructible, polynomials arose and their irreducibility was needed. So let's now see how we can prove that these polynomials are irreducible. Now from ring theory, we may remember a sufficient condition for such irreducibility, namely the Eisenstein criterion. So you may want to use that if it is usable, that is, if the hypothesis of Eisenstein's criterion are satisfied, then we may conclude that the polynomial is irreducible. Unfortunately, that cannot be done here. For example, for this first one, let's recall for that matter for a moment the Eisenstein's criterion. What that criterion said is that, say, we have a polynomial with integer coefficients. That means these ai's are all integers. And suppose there is a prime number p which divides all these coefficients except the leading one. That means p divides all the ai's, but p does not divide the leading coefficient an. Also, additionally, the square of p does not divide this a0, a0. Then the polynomial is irreducible over Q, the field of rational numbers. Here, however, there is no point in trying to see if this is true, because no prime can divide this a0. A0 in this case is -1, so it's not divisible by any prime. So Eisenstein's criterion cannot be applied here. Instead, we will prove its irreducibility by assuming that it's reducible and then arriving at a contradiction, that is from scratch. So suppose (8x cubed minus 6x minus 1) is reducible over Q. By Q we of course mean the field of rational numbers. Then the polynomial will have a root that is a rational number, because that's what reducibility means or is equivalent to. Then the polynomial has a root, say r, in Q. That means r is a rational number which if you substitute for x, you are going to get 0. So since r is a rational number, r can be written as a quotient of two integers where a and b are integers. Okay, so normally what we will do, we would write z, right? But in this book, the set of integers is being denoted by capital J. If you want, you can write z or z, okay, but I'm just maintaining what is there in the text. Now what I do is that I also assume that a and b are non-zero. B of course is non-zero, that is always there. However, a is non-zero, and by mentioning this, I mean that r is non-zero. Why? Because r equal to 0 is anyway not a root of this. If you substitute 0 for x, you are going to get -1, not 0. Okay, so without assuming without losing anything, I can assume that r is non-zero, and hence both a and b are non-zero. And another condition can be assumed that a and b are relatively prime, that their GCD is 1. There is no common factor because you can cancel the common factors out and then you will have this. Now if you substitute this r, which is a over b here, then you will get 0. So from that we are going to get some things. A cube over b cube minus 6x. So 6a over b minus 1 will be equal to 0. Now if you multiply both sides by b cube, you will get 8a cube minus 6ab square minus b cube is equal to 0. Now from this, of course, you can do one of these two things, and here what I have done is I have written it in this way. A divides b cube. Okay. So if we take b cube on that side, that means add b cube on both sides. You can then do this. You can take a common out, so that gives you this. So this is whatever it is, it's after all an integer, right? Because a and b are integers, and additionally now see a is non-zero. So this equation tells us that a divides b cube. Thus, a divides b cube. But we have this condition also, right? Since a and b are relatively prime, so combining this and this, what is our conclusion? Our conclusion is that a can be either 1 or -1. If a is allowed to be negative, that is okay. So a can be -1 also, and that's how you will get two possibilities. We have a plus or -1. And accordingly, now the equation will reduce to this. So say a is +1. Let us consider that value first. Then what do we get? 8 minus 6b square equal to b cube, which is the same as 8 equal to 6b square plus b cube, which is the same as 8 equal to b times 6b plus b square. Or we have that other possibility also, right? A can be -1. Now if a is -1, then -8 plus 6b square is equal to b cube, which is equivalent to 8 equal to 6b square minus b cube, and which is equivalent to 8 being equal to b times 6b minus b square. And this implies, I mean, whatever the case is, we can see that from this equation and also this equation that b divides 8, right? Now from such an equation, say, okay, let me just bring this point also. You see an equation like this where you have only integers. Now from that itself you cannot conclude that, say, one factor here divides the other. The additional condition that that factor is non-zero should also be taken into account, because 0 does not divide anything, okay? But b is non-zero, so that's why we can conclude this. This implies b divides 8. So what are the possibilities for b? And so b must come from this set, because these are the only divisors of 8. And correspondingly, now taking everything into account, that these are the only values of b, and also a can be either 1 or minus 1, what happens to r? Obviously r has these possible values, because r is a over b. But now this itself is a contradiction, because none of these real numbers, in fact they are all rational, so let me write like that itself. However, none of the rational numbers is a root of our polynomial. That means 8x cubed minus 6x minus 1, and this is just simply a computational task. You have to put each one of these values in place of x and see that you won't get 0. Okay, so none of them is a root, but then we have got a contradiction, because we have supposed that r is a root, and then we have concluded that r must be one of these values, and none of these values is a root, so that is a contradiction. This contradiction proves that our supposition is wrong. i.e., the polynomial, the given polynomial is irreducible over the field of rational numbers. So that is part A. In part B, we do something else. You see, here also we have used the fact that reducibility of a polynomial is equivalent to the polynomial having a rational root. In other words, if the polynomial has no rational root, then the polynomial cannot be reducible. That means it will be irreducible. Now, in the second polynomial, luckily we can write all the three roots. It's a cubic polynomial, so it will have three roots. We can write all the roots down. It's easy. So that's why looking at those roots and looking at the fact that none of them is a rational number, it will immediately imply that the polynomial is irreducible over q. And the polynomial, of course, is x cubed minus 2. So that means its roots are the three complex cube roots of 2. And we know them. Okay. The roots, and they can of course be written in terms of the complex cube roots of unity. In general, such a statement would be incomplete if we just simply write the roots of x cubed minus 2 is, I should not have said is, are these. But here, in the context of the things that we are doing, these are polynomials over the field of rational numbers. And we know that any such polynomial is going to have all of its roots complex numbers. Okay, so that's why nothing else needs to be said. The roots of these are, otherwise ideally I should have written the roots of this in C in the field of complex numbers are cube root of 2, and this is the real cube root of 2, which exists, of course. It's a fact from real analysis. And then you multiply this with one of the two complex non-real cube root of unity, and the other one then is this. So these things are your omega and omega square. Okay, and they all lie outside the field of complex numbers. Rational numbers. This one is not rational. That is the fact that we already know. And these others are not even real. How can they be rational? So we can directly conclude that this is irreducible over the field of rational numbers. And now we come to the last one, which is similar to this first one. Suppose x cube plus x square. If you are wondering why two different approaches, it's because for these other polynomials, it's somewhat difficult to find the roots, the exact roots. This one, however, is immediate. That's why. Suppose this is reducible. Here also you can see that because of this minus 1, we cannot possibly apply the Eisenstein's criterion. Then same, just like part A, then the polynomial has a root r in Q. Let R be A over B, where A and B are non-zero integers that are relatively prime, that is their GCD is 1. And then again, just like part A, you substitute A over B for X and you will get 0. So A cube over B cube plus A squared over B squared minus 2 times A over B minus 1 is equal to 0. So again, multiply both sides by B cube, that will give you this. Alright, now here what kind of divisibility, it's almost the same, so you can either divisible by A or divisible by B, but which one have I done? Oh, so I consider divisibility by B first. Alright, so let's keep A cube on one side and take the others to the other side. So that gives me minus A squared B plus 2AB squared plus B cube, or minus A squared plus 2AB plus B squared. Again, because all the things are integers and B is non-zero, so B divides A cube, and since A and B are relatively prime, so B is either plus 1 or minus 1. So now this equation, or rather here itself you can consider, because B is going to vanish, right? B will vanish means of course two cases will come according as B is plus 1 or minus 1. So we are going to get one of the equations, this A cube plus A squared minus 2A minus 1 is equal to 0, but let me just directly write 1, okay, or if B is minus 1, then we will get minus A cube, this one will not change, plus A squared, this one will change, plus 2A and minus 1 of course is minus 1, which can be taken on that side. So whatever the case is, whether this is true or that one is true, now A has to divide 1, because that's what we get from these equations. And so A is plus 1 or minus 1. Thus, so B is plus 1 or minus 1, A is also plus 1 or minus 1, and our R is A over B. So R is also either plus 1 or minus 1. However, neither -1 nor 1 is a root of the given polynomial. So the rest is same. So our supposition is wrong, i.e. the given polynomial must be irreducible over Q. So that part of course I am not writing. So this is our solution. Now let's see the next one, 8. And I think I need a little ink. In exercise 8, okay, so someone may wonder what can a possible root of this polynomial be, that is this one, this third one. Then the next exercise is about that itself. Prove that two cos 2 pi over 7 satisfies that polynomial. Minus 2x minus, it's the same polynomial, no? X cube plus a, yeah. And a hint is also given. The hint draws our attention to the relationship between trigonometric functions and complex numbers. Use this fact, the author says. We know an expression for the cosine of a real number in terms of complex exponential function, right? And that thing is the e to the power 2 pi I over 7 plus e to the power minus 2 pi I over 7. So what the author is asking us to use this expression and use this complex number in place of x here and calculate the value of the polynomial, that is expand doing all those things. We however will not do that, okay? Instead we will do something else. So what we do, first we give the real number 2 pi over 7 in names, say call it theta. Then you can see that 7 theta will be equal to 2 pi. So 3 theta will be 2 pi minus 4 theta. And so we then directly write this. Cos 3 theta is equal to cos 2 pi minus 4 theta, because if you add 4 theta, forget about cosine for a moment, okay? Does that mean that 3 theta is equal to 2 pi minus 4 theta? Yes, because if you add 4 theta on both sides, you are going to get 7 theta equal to 2 pi, which is true because theta is 2 pi over 7. But now if you use the usual trigonometric formula, say cos a minus b expansion, if you use, and you use the fact that cos 2 pi is 1 but sin 2 pi is 0, then you just get this. This is equal to cos 4 theta. Okay, so cos 3 theta is equal to cos 4 theta for this theta. Now we are going to use some trigonometric identities which I am sure you are all familiar with. Cos 3 theta equals 4 cos cube theta minus 3 cos theta. But what about cos 4 theta? Well, you can use the double angle formula. You have to use it 2 times in order to get an expression involving only theta and not its multiples. However, there will be some squaring things involved. So if you do all those things, for example, first, so what is it that you have here? Cos 2 times 2 theta. So that will be 2 cos square 2 theta minus 1. And then in place of that cos 2 theta, you can again write 2 cos square theta minus 1. Then you have to you have to expand the square, do all the calculations. So if you do that, you will get this 8 cos to the power 4 theta minus 8 cos square theta plus 1. It's just a matter of calculating the thing. Okay, so what are we getting? 4 cos cube theta minus 3 cos theta is equal to this. Now let's bring all the things to one side. So that gives us, and if we arrange things according to the exponents of these powers, then we get this 8 cos to the power 4 theta minus 4 cos cube theta minus 8 cos. It would have been nice if I wrote this thing like this, no, but anyway, plus 1. Oh, we have 1 cos theta also. Okay, I cannot forget that. Plus 3 cos theta because it's on that side, and on this side we have plus 1. That should now be equal to 0. And the thing is that this expression, this polynomial in cos theta, can be factorized like this. Cos theta minus 1 times 8 cos cube theta plus 4 cos square theta minus 4 cos theta minus 1. This product should be equal to 0. Now this angle is an angle for which cos theta is not equal to 1 because it's an acute angle, we can see that, and in this region cos theta does not become 1. Why? Oh, by the way, why is it not 1? That's because if you, for a moment, if you think about the cosine function, if you think about the cosine function means if you think about the graph of the cosine function, because that's the way of remembering how the function behaves, right? So suppose you have 0 here and you have pi over 2 here and then you have pi here. Say this is 1. So cosine of 0 is 1, cosine of pi over 2 is 0, and then it becomes negative. So the graph goes like this, right? At pi it becomes minus 1. And what is our 2 pi over 7? Where does this 2 pi over 7 lie? Is it less than pi over 2? It's of course greater than 0. Yes, because 4 pi is less than 7 pi. So it is here somewhere. And obviously it's not 1 because in this region it becomes 1 only at 0. Okay, so that's why cos theta is not equal to 1. So that means this factor is non-zero. So the other one must be 0. So this implies, let me write here, 8 cos cube theta plus 4 cos square theta minus 4 cos theta minus 1 is equal to 0. Since cos theta is not equal to 1. But now if you look carefully, you will see this from this final equation. Note that the above equation can be written as this. Two cos theta whole cube plus 2 cos theta whole square minus 2 times 2 cos theta minus 1 equal to 0. Thus 2 cos theta, which also is nothing but 2 cos 2 pi over 7, is a root of or satisfies that polynomial same meaning x cube plus x square minus 2x minus 1, and that's what we had to show, right? Now you may of course question this approach. The first point of objection would be that how would you know that you have to do these things? And the answer is no, I don't know. Okay, I came up with this, and that's how I liked this solution, and that's why I did it. Instead, you can take the direct approach given in the hint. You just use this fact and calculate all the things, and then finally figure out that you get 0. Okay, you can do that. It's up to you. So these things are fine, but let us now in the next exercise recall something that we did in the previous video. Namely, we proved that an angle theta is constructible if and only if cos theta, that real number, is constructible. Now we are going to apply this result in this exercise. Prove that a regular pentagon is constructible. Proving this is equivalent to proving that the angle 2 pi over 5 radian is constructible, and that, because of what we did in the previous video, is equivalent to proving that cos 2 pi over 5 is constructible. Okay, so that's what we now want to do. We prove that this is constructible. Okay, if it feels like it's a pain to every time write is constructible, you can also use the other way of writing this, that this thing belongs to capital W, because by capital W the author means the field of constructible numbers. So that way also you can write. So like before, let theta be 2 pi over 5, and now we are going to go through similar steps that we have seen here just now. Or if you want, you can use that complex number identity expression for cos 2 pi over 5, and that way also you can approach. However, see, that way also you can approach, I am saying, but you do not have the polynomial here, no? So that's why now you will realize why this approach is somewhat better. Then cos 2 theta, because this approach will automatically give you the polynomial. There is one catch though. You won't really realize in the beginning itself what to keep, how much of theta to keep on this side and how much should be transferred to the other side, but with trial and error you will figure out. Okay, now from properties of the cosine function, cos 2 theta is also cos 2 pi minus 2 theta. Again, use cosine of a minus b formula and you will get this. Or this is a fact that we already know from trigonometry. And now this is equal to cos 3 theta. Why? Because 2 pi is equal to 5 theta. So 2 pi minus 2 theta should be equal to 3 theta. And that's what we have done. Since 2 pi minus 2 theta is 3 theta, so we have applied cosine to both sides. And that's how we have got this. And now let's use the trigonometric identities. Here we do not have that problem of 4 theta. The angles are only double angle and triple angle. Okay, so the left side is 2 cos square theta minus 1, and the right side is 4 cos cube theta minus 3 cos theta. And now if you take all the things on one side, then we get 4 cos cube theta minus 2 cos square theta minus 3 cos theta plus 1 equal to 0. And here also I think there is a factorization is involved. Cos theta minus 1 times 4 cos square theta. You please verify these calculations, okay, and let me know. Hopefully I haven't made any mistake, but still let me know that I am correct. This is equal to 0, and just like before, cos theta in this case is also not equal to 1. And as such, that other factor will be 0, and that will give us a polynomial. Since cos theta is not equal to 1, we have from the above equation this 4 cos square theta plus 2 cos theta minus 1 equal to 0, or okay. No, I did not, okay, after this I did not do this, however, now only I see that this can also be done. I mean, instead of dealing with only cos theta, we can deal with cos 2 theta also. That way the polynomial will be somewhat easier. But anyway, let me just do what I have done here. Thus, cos theta satisfies the polynomial 4x square plus 2x minus 1 in the polynomial ring qx, that is it's a rational polynomial. Now next comes the question of its roots. Why its roots? Because you see, just now we have shown that cos theta is a root of this polynomial, and it's a quadratic polynomial, so it's a simple matter to find its roots. We have formula for that. So from that we will be able to determine what cos 2 pi over 5 actually is, what real number it is. Has roots. There will be two roots, and those two roots are these. From the ordinary quadratic polynomial root formula, you will get the this is not 2 because we already have 4 here, so it should be, well, 8 will come in the denominator, but after cancellation you will have 4. However, cos theta has been proved to be a root, and theta is 2 pi over 5, and for that value cos theta is not negative. So since cos theta is positive, from all these things we must have cos theta equal to root 5 minus 1 over 4. Now, is this number constructible? That's the question. It is constructible, and it will come from that our main result theorem, I think it was theorem 541. Let's recall theorem 541. What was it? Say you are given a real number alpha. Alpha is constructible if and only if you can find those real numbers lambda I, okay, such that lambda 1 square belongs to the field of rational numbers, and lambda I square belongs to this extension of Q obtained by adjoining the previous lambdas. Alright, and finally, well, here I will vary from 1 to n actually. Okay, so that the last real number lambda n, its square should belong to Q of the previous things. Okay, that extension obtained from Q by adjoining all the previous lambdas. And finally, this alpha should belong to this final extension. And that's how we are able to show that square root of 5 itself is a constructible number. Okay. Do not confuse constructible numbers with algebraic numbers. Okay, that's a different thing. So let's write like this: since this and square root of 5 itself belongs to this, we have root 5 belonging to the field of constructible numbers, or if you want you can write in words also, and that is why root 5 is constructible. Do you see how this has been used here? What is lambda in this case? I mean, what is the first lambda in this case? The first lambda in this case is root 5 itself, and root 5 is your lambda 1. Why? Its square is a rational number, it is 5. And what is there is another lambda 2. Lambda 2 is also root 5. Okay. Do we really need to go, do we really need lambda 2 here? Or does the process stop at lambda? Okay. There is no need to consider lambda 2. Just one lambda 1 is enough. How many lambdas we will need in theorem 541, that is up to us, right? So say my list is just this single lambda 1, which is root 5. Are these conditions true for this lambda? The first condition of course is true, and there is no other condition like that after that, because there is no other lambda with higher suffix value. Okay, no lambda 2 or lambda 3. This final condition, however, should be true. That is, whether our real number belongs to the extension of Q obtained by adjoining all the lambdas. All the lambdas means in this case there is only one lambda. So the extension is this. And root 5 of course belongs to this by definition of that extension. This is the smallest field containing both Q and root 5. And that's why from this theorem 541, root 5 is a constructible number. You can mention that this is coming from that theorem here by theorem 541. So this also belongs to W. Okay, and then how is this, where is this coming from now? W belongs to, root 5 belongs to W. Minus 1, 4, these things also belong to W. Why? Because these are rational numbers. In fact, they are integers. And W being a subfield of the field of real numbers contains all the rational numbers in it. So that's why this expression also belongs to W. But that's it, that's what we have to show, because here theta is cos 2 pi over 5. That is constructible, so 2 pi over 5 is constructible, and that's why a regular pentagon is constructible. And let's see another one of this type, the next one, and then we will stop. Prove that. This one is much easier, it's almost instant. Prove that the regular hexagon is this one is easier because here the cosine value is a known value and is a very easy value. Since we are dealing with a hexagon, so now we have to look at this cosine of 2 pi over 6, which is cosine of pi over 3, which is just 1 over 2. It's a rational number, and the field of rational numbers is contained in the field of constructible numbers. So that's how it's instantaneously we are getting this. Two pi over 6 is constructible, and that's why a regular hexagon is constructible. Alright, so I'm ending the video here, but there is still a question about these things that I haven't quite addressed. It's that a regular hexagon, say this one, is constructible, okay, like this. So the internal angle of a regular, what I'm trying to say is that if you draw the diagonals of a hexagon, okay, then they will meet at a central point, so to speak. So you can imagine that that those lines are emanating from the central point of the hexagon and meeting all the vertices of the hexagon. So the internal angles that you get, each such angle is 2 pi over 6, because all of them will be equal. Now we have proved that that angle is constructible. So using straightedge and compass you can construct that angle. But then from that angle, how can you construct the hexagon? That question is there, but I leave that question to you to figure out. Okay, so with that we are over for tonight, and tomorrow we have our usual upload. And since we have already gone through the group exercises recently from Gallian, so tomorrow let's go to the ring problems from Gallian. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.